Deep in the fabric of space, where the laws of physics twist and bend, lies one of the cosmos' most enigmatic secrets: black holes that might have existed since the very dawn of time itself. Picture this: tiny, ancient monsters lurking in the darkness, forged not from collapsing stars, but from the chaos of the universe's birth. These are primordial black holes, and they could rewrite everything we thought we knew about the origins of our reality. While most black holes form from the violent deaths of massive stars, primordial black holes are something far stranger: hypothetical relics from the universe's earliest moments, when density fluctuations in the searing hot soup of the Big Bang itself might have collapsed into these mysterious objects. Some could be as small as an atom, others as massive as a planet, and they might be hiding in plain sight, weaving through the cosmos undetected. What if I told you these elusive cosmic shadows could hold the key to some of astronomy's biggest puzzles? From the nature of dark matter to the bizarre ripples in space-time we call gravitational waves, primordial black holes might be the missing piece we've been searching for. And that's just the beginning. Over the years, scientists have proposed 30 mind-bending theories about these ancient anomalies, each more fascinating than the last. Some suggest they could be crashing into neutron stars, setting off cosmic fireworks. Others speculate they might even be responsible for seeding the very first galaxies, sculpting the universe as we know it. And then there's the wildest idea of all. What if primordial black holes aren't just cosmic oddities, but actual doorways to other dimensions? Today, we're diving into these 30 electrifying theories, peeling back the layers of one of space's greatest mysteries. Whether they're lurking in our solar system, distorting distant starlight, or even influencing the fate of the universe itself, primordial black holes challenge everything we thought we understood. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. Are these phantom relics real? And if they are, what secrets are they keeping? Let's find out. One of the most tantalizing theories about primordial black holes suggests they could be the invisible architects of the cosmos, hidden in plain sight as the mysterious substance we call dark matter. Think about it. For decades, astronomers have known that the universe holds far more gravity than what visible matter can explain. Galaxies spin too fast, light bends in ways it shouldn't, and clusters of stars move as if bound by some unseen force. We've labeled this ghostly influence dark matter, but its true identity remains one of science's greatest enigmas. Here's where primordial black holes enter the picture. Unlike ordinary black holes, which form from dead stars and are relatively rare, these ancient relics could be scattered everywhere, silent, undetectable, and abundant enough to account for dark matter's gravitational grip. Some researchers argue that if the early universe birthed countless tiny black holes, each no heavier than an asteroid but as compact as a marble, their combined mass might solve the dark matter puzzle without requiring exotic new particles. The math is compelling. Simulations show that a population of primordial black holes with masses between a few tons and several moons could weave through galaxies without disrupting starlight or gas clouds, leaving only gravity as their calling card. They'd be too small to swallow stars whole, too faint to emit detectable radiation, yet collectively massive enough to sculpt the universe's structure. Even more intriguing, their existence would neatly sidestep one of dark matter's biggest headaches: the decades-long failure to spot hypothetical particles like WIMP in underground detectors. But how do we test such a radical idea? Astronomers have turned to ingenious methods. Some hunt for fleeting flashes of light when a primordial black hole passes in front of a distant star, briefly magnifying its glow like a cosmic magnifying glass. Others listen for the faint echoes of black holes colliding, their mergers sending ripples through space-time that gravitational wave observatories might catch. And then there's the wild card: what if these black holes occasionally punch through dense objects like neutron stars, triggering explosive shock waves that telescopes could spot. The implications are staggering. If primordial black holes are dark matter, it would mean the universe's missing mass isn't some intangible particle but actual, tangible objects, frozen remnants of creation itself. It would rewrite textbooks, reshape our search for dark matter, and perhaps even explain why some galaxies seem to form earlier than physics currently allows. Of course, not all scientists are convinced. Critics point to gaps in the theory, like the lack of direct observational proof or the challenge of explaining how these black holes could form in just the right numbers. Yet the allure remains. Whether they're the hidden hand behind dark matter or just another cosmic red herring, primordial black holes force us to rethink the fundamental nature of reality. And that's the beauty of this mystery. Every unanswered question is an invitation to dig deeper, to peer into the shadows where the universe guards its oldest secrets. While most black holes emerge from the dramatic collapse of massive stars, primordial black holes might trace their origins to an even more spectacular event: the universe's own explosive birth. Picture the cosmos in its first fleeting moments, a seething cauldron of energy undergoing a growth spurt so violent it stretched space itself faster than light could keep up. This was cosmic inflation, a fraction of a second frenzy that could have sown the seeds for black holes to form in a way no star ever could. According to this theory, the rapid expansion didn't just smooth out the universe. It might have also created tiny wrinkles in space-time, pockets where matter became so densely packed that they collapsed under their own gravity before stars even had a chance to exist. Imagine bubbles forming in boiling water, but instead of popping, these cosmic bubbles squeezed themselves into black holes. Some could have been as light as a paperclip, others as hefty as a mountain, all forged in the furnace of inflation's aftermath. What makes this idea so revolutionary is how it flips traditional astrophysics on its head. Normally, black holes need the extreme pressure of a dying star's core to trigger their formation. But inflation-era black holes would have bypassed that entirely, appearing spontaneously from the turbulent energy of the newborn universe. This challenges our understanding of how gravity behaves under such extreme conditions, suggesting that the laws of physics might have worked differently when the cosmos was just a trillionth of a second old. The consequences ripple across modern cosmology. If inflation did spawn these black holes, they'd be far more numerous than stellar-born ones, potentially solving mysteries like dark matter or the unexpected heft of early galaxies. Some simulations even suggest these ancient black holes could have acted as gravitational anchors, pulling together the first clumps of matter to kickstart galaxy formation. Yet proving this theory is like trying to find smoke from a fire that burned out 14 billion years ago. Scientists scour the cosmos for indirect clues, anomalies in the cosmic microwave background, strange gravitational lensing patterns, or even peculiar frequencies in gravitational wave detectors. Each potential signature is a whisper from the universe's infancy, hinting at whether inflation truly was the cosmic black hole factory we've been searching for. What's startling is how much hangs in the balance. If primordial black holes did form during inflation, it would mean our universe's structure, from the largest galaxy clusters to the voids between them, might owe its existence to these microscopic time capsules. They wouldn't just be relics of the early universe, they'd be its architects, quietly shaping everything we see today. And that raises an even wilder question. Could the universe we know have turned out differently if just a few more or fewer of these black holes had formed in those first chaotic moments? The answer might be hiding in the darkness between the stars. Another cosmic puzzle that primordial black holes might help solve revolves around the missing baryon problem, a mystery as baffling as it is fundamental. Baryonic matter, the ordinary stuff that makes up stars, planets, and even us, seems to vanish when we take a cosmic inventory. scientists estimate that nearly half of the universe's expected baryons are unaccounted for, hiding somewhere between galaxies in forms we can't easily detect. But what if these missing baryons aren't just floating in diffuse clouds or hiding in plain sight? What if they've been swallowed by an invisible population of primordial black holes? The idea hinges on scale. While stellar mass black holes are too sparse to explain the discrepancy, countless smaller primordial black holes, some no larger than a baseball but as massive as a mountain, could have spent billions of years gobbling up baryonic matter without leaving a trace. Unlike their star-sized cousins, these tiny gravitational traps wouldn't emit dramatic X-ray jets or warp spacetime enough for easy detection. Instead, they'd act like cosmic sponges, silently absorbing gas and dust from their surroundings. Over eons, even a modest number of these objects could have siphoned off enough material to account for the missing baryons we've been searching for. Supporters of this theory point to the way primordial black holes might interact with large-scale cosmic structures. For example, filaments of gas stretching between galaxies, the so-called cosmic web, could be littered with these minuscule black holes, their gravity subtly altering how matter flows through these vast bridges. Simulations suggest that if primordial black holes were common in the early universe, they could have redirected baryonic matter into unexpected pockets, making it appear missing when we survey the cosmos today. But here's where it gets even stranger. Some researchers propose that these black holes didn't just hide baryons, they might have recycled them. Quantum mechanics tells us that black holes slowly evaporate over unimaginable timescales, leaking energy back into space. If enough primordial black holes have been decaying since the dawn of time, their gradual demise could have released baryons in unfamiliar forms, dispersing them so thinly that our telescopes can't pick them up. It's a cosmic sleight of hand where matter isn't truly gone, just transformed. Critics, however, raise valid concerns. If primordial black holes had feasted on baryons so aggressively, why don't we see more evidence of their meals? The answer might lie in their stealth. Tiny black holes could avoid the telltale radiation bursts of larger ones, leaving only subtle gravitational fingerprints. New telescopes designed to map the cosmic web in unprecedented detail might finally spot these anomalies, revealing whether primordial black holes are the universe's ultimate matter hoarders. What's at stake isn't just a bookkeeping fix for the cosmos. If this theory holds, it would mean that baryonic matter, the building blocks of everything familiar, has been playing an elaborate game of hide and seek, with primordial black holes as the unseen referees. It would reshape our understanding of how matter flows through the universe, how galaxies assemble, and even how long the cosmos can keep shining before its fuel runs out. And that raises a humbling thought. If so much ordinary matter has been hiding in black holes all along, what else might we be overlooking in the vast, uncharted dark? At the quantum level, reality behaves in ways that defy common sense. Particles blink in and out of existence. Energy fluctuates unpredictably, and empty space teems with invisible activity. Now imagine this microscopic chaos writ large across the entire infant universe. According to one compelling theory, these subatomic tremors could have sown the seeds for primordial black holes, transforming quantum hiccups into gravitational monsters. Here's how it might have happened. In the universe's first microseconds, space wasn't smooth and calm. It was a turbulent quantum foam where energy densities fluctuated wildly. At these scales, Heisenberg's uncertainty principle allowed particles and energy to appear and vanish spontaneously. Most of these quantum bubbles would have fizzled out instantly, but under the extreme gravity of the early cosmos, some fluctuations could have crossed a critical threshold. Picture a wave cresting just high enough to collapse under its own weight, except instead of water, it's a knot of space-time and energy so dense it forms a black hole. This idea thrills physicists because it bridges two seemingly disconnected realms, quantum mechanics and gravity. Normally, These frameworks operate at vastly different scales, but primordial black holes born from quantum fluctuations would be a rare phenomenon where both forces leave their fingerprints. The math suggests these black holes could span an astonishing range of sizes from subatomic specks, weighing less than a grain of sand, to behemoths rivaling asteroids, all depending on when and where the fluctuations occurred in the universe's expansion. What makes this theory so elegant is how it leverages existing physics without requiring exotic new ingredients. Inflation, the rapid expansion thought to have shaped the early cosmos, would have stretched quantum ripples across vast distances. Some regions, randomly denser than others, could have reached the tipping point for collapse. It's like blowing up a balloon with tiny wrinkles as it inflates. Some creases deepen into folds while others smooth away. In this cosmic scenario, the deepest folds become black holes. Critically, these quantum-born black holes would differ from their stellar counterparts in one key way: their distribution. Instead of being confined to galaxies, they'd be scattered everywhere, a diffuse gravitational fog left over from the universe's quantum infancy. This could explain why efforts to locate dark matter in galactic halos keep coming up empty. If dark matter is actually a swarm of these ancient quantum relics, they'd be invisible yet omnipresent, woven into the fabric of space itself. The hunt for evidence is pushing astrophysics to its limits. Researchers analyze the cosmic microwave background for anomalies that might betray early black hole formation. Others simulate quantum fields under extreme conditions to see if fluctuations can realistically produce black holes. And then there's the tantalizing possibility that some of these objects might still exist today, drifting through our solar system and occasionally distorting starlight or triggering unexplained gravitational waves. But perhaps the most profound implication is philosophical. If true, this theory would mean black holes aren't just stellar graveyards or galactic engines. They're quantum accidents frozen in time, cosmic fossils preserving a snapshot of reality when it was barely a heartbeat old. They'd be reminders that the universe's grandest structures might owe their existence to the tiniest, most fleeting whispers of quantum chaos. And if we ever find them, it won't just illuminate the origins of black holes. It could reveal how the quantum and cosmic scales intertwine to shape everything we see. Now let's shrink our perspective down to the very limits of reality, where the universe operates on scales so tiny, even atoms seem gargantuan. Some theories suggest primordial black holes might not just be small, but unimaginably small, surviving relics from the instant of creation itself. Picture an object so compact that 1,000,000 billion of them could line up across a single proton, yet each packing the mass of a mountain. These hypothetical Planck-scale black holes would push physics to its absolute edge, existing in a realm where space and time cease to behave as we know them. The Planck length, about 1.6 times 10 to the negative 35th meters, is nature's smallest possible unit of distance, a boundary beyond which the classical concepts of space dissolve into quantum froth. If black holes formed at this scale in the universe's first sliver of a second, they'd defy everything we expect from cosmic objects. Unlike their stellar-sized cousins, these microscopic anomalies wouldn't grow by devouring matter. Instead, quantum mechanics dictates they'd evaporate, leaking energy in faint bursts predicted by Stephen Hawking's famous radiation theory. But here's the twist: the tinier the black hole, the faster it evaporates. A Planck-scale black hole might vanish in less time than it takes light to cross its own diameter, popping out of existence almost as soon as it forms. Yet some physicists speculate that a fraction of these fleeting objects could have survived, perhaps stabilized by extra dimensions, exotic quantum effects, or even errors in our current understanding of Hawking radiation. If so, they'd be drifting through the cosmos right now, invisible yet omnipresent, like cosmic dust forged in the Big Bang's furnace. Their existence would rewrite the rules of quantum gravity, offering clues to how Einstein's relativity and quantum mechanics reconcile at these extreme scales. Detecting such relics would require rethinking physics itself. Traditional telescopes are useless against objects smaller than atoms, but scientists have proposed wild workarounds. Some suggest these black holes might occasionally collide with dense materials like neutron stars, producing unique vibrations or heat signatures. Others theorize their evaporating final moments could release bursts of high-energy gamma rays, a last gasp detectable by sensitive instruments. There's even the spine-tingling possibility that Planck-scale black holes could be artificially created in particle colliders, offering a lab-made window into the universe's birth. The implications ripple far beyond curiosity. If Planck relics exist, they'd be fossilized snapshots of the universe's first quantum fluctuations, holding data about conditions we can't otherwise access. They might also solve lingering paradoxes, like why the cosmos didn't immediately collapse into a sea of black holes after the Big Bang. Perhaps most tantalizingly, they could be the missing link in theories of everything, proving that space-time itself is pixelated at the smallest scales. Of course, skeptics abound. Without direct evidence, Planck-scale black holes remain a beautiful thought experiment, one that dances on the knife's edge between genius and speculation. But that's the thrill of cosmology. Sometimes the wildest ideas, tested against the harsh light of math and observation, reveal truths stranger than fiction. And if we ever do find proof of these quantum ghosts, it won't just confirm a theory, it'll crack open a door to the universe's most guarded secrets, hidden in plain sight since time began. Stephen Hawking's groundbreaking theory didn't just revolutionize our understanding of black holes, it turned them from eternal traps into ticking clocks. For primordial black holes, especially those tiny enough to fit on a pinhead, this cosmic countdown could mean their entire existence is a fleeting whisper in the dark. Hawking radiation, the eerie glow of particles escaping a black hole's grip, suggests these objects aren't the indestructible monsters we once imagined. Instead, they're slowly leaking energy, shrinking over time until they vanish in a final, explosive puff of radiation. But here's where it gets fascinating for primordial black holes. Unlike their stellar counterparts, which take longer than the current age of the universe to evaporate, the tiniest primordial ones could be burning out right now. A black hole with the mass of an asteroid might last billions of years, but one as light as a mountain could evaporate in less than the span of human civilization. The smaller they are, the hotter they glow, and the faster they disintegrate. Imagine a cosmic version of a sparkler, fizzling brighter and faster the smaller it gets until it winks out entirely. This evaporation process isn't quiet. As these black holes approach their end, they're theorized to unleash a burst of high-energy particles, gamma rays, neutrinos, and even exotic particles we've yet to discover. Astronomers have spent decades scanning the skies for these telltale flashes, hoping to catch the dying moments of a primordial black hole. Some even speculate that certain unexplained gamma-ray bursts, those brief but brilliant cosmic fireworks, might not be distant stellar explosions at all, but the last gasps of these ancient relics. Yet Hawking radiation does more than just doom tiny black holes. It could solve one of the universe's quirkiest mysteries, the missing primordial black holes. If the early universe spawned countless micro-black holes, most should have evaporated by now, leaving behind a diffuse sea of radiation. This cosmic background of evaporated holes might already be hiding in plain sight, woven into the static of the universe's microwave afterglow. Others might be lingering just on the brink of destruction, their faint Hawking glow blending into the noise of interstellar space. The stakes couldn't be higher. Detecting even one evaporating primordial black hole would confirm Hawking's theory in a way no lab experiment ever could, proving that black holes aren't just cosmic vacuum cleaners but dynamic objects governed by quantum mechanics. It would also offer a glimpse into the universe's earliest moments, revealing how wildly conditions fluctuated in that primordial soup, and if we find none. That absence would be just as telling, forcing us to reconsider how black holes form, or whether they truly do fade into nothingness after all. But the real magic lies in the paradox. These black holes, forged in the most violent birth imaginable, might meet their end not with a bang, but with a whisper, a silent pop of particles carrying secrets from the dawn of time itself. Whether they are out there or not, their ghostly presence reminds us that the universe's oldest mysteries often lurk in the smallest, most fleeting corners of reality. At the heart of nearly every galaxy, including our own Milky Way, lurks a gravitational monster, a supermassive black hole millions or even billions of times heavier than our Sun. But here's the catch: these cosmic giants appear too soon in the universe's timeline. Some quasars' bright beacons powered by supermassive black holes shone when the universe was less than 1 billion years old, leaving scientists scratching their heads. How could black holes grow so massive, so fast? The answer might lie in the universe's first moments, with primordial black holes acting as ready-made seeds for these galactic titans. Imagine a cosmic shortcut. Normally, a black hole starts as a collapsed star, slowly growing by swallowing gas and merging with others over eons. But for supermassive black holes to exist in the infant universe, that process would need a head start. Enter primordial black holes, some of which could have formed with masses hundreds or thousands of times that of our Sun, bypassing the slow stellar growth phase entirely. These heavyweights would have had a gravitational advantage from day one, pulling in surrounding matter far more efficiently than their stellar-born cousins. The math is compelling. Simulations show that a primordial black hole drifting into a dense cloud of early universe gas could balloon in size at astonishing rates. With no competition from stars or galaxies yet formed, it could feast unimpeded, doubling its mass in mere millions of years, a blink in cosmic terms. Some models suggest these seeds might have grown 1,000 times faster than conventional black holes, hitting supermassive status just in time to power the quasars we observe in the distant universe. Observational clues add weight to the theory. The James Webb Space Telescope has spotted supermassive black holes in galaxies so ancient they shouldn't exist under traditional formation models. Their sheer size at such early epochs hints at a jump start, and primordial black holes fit the bill perfectly. Even more telling are the oddball black holes we've found in the present-day universe, ones too large to have grown from stellar collapses alone, as if they arrived pre-loaded with extra mass. Critics raise valid questions, of course. If primordial black holes seeded all supermassive black holes, why do some galaxies lack them? And why haven't we detected intermediate-sized black holes, the missing link between primordial seeds and their gargantuan descendants? Supporters counter that mergers and chaotic early conditions could explain these gaps, scattering or erasing evidence of the seeds over time. The implications stretch beyond black hole origins. If this theory holds, it means the universe's largest structures might owe their existence to microscopic density fluctuations from the Big Bang, a direct line from quantum jitters to galactic empires. It would rewrite the story of galaxy formation, suggesting that black holes didn't just grow within galaxies but helped build them from the inside out, their gravity sculpting stars and gas into the majestic spirals and ellipses we see today. And that leaves us with a humbling thought. The behemoths at the centers of galaxies, shaping cosmic evolution for billions of years, might just be the grown-up versions of the universe's very first black holes, time travelers from an era when reality was still taking shape. Whether this theory stands or falls, it forces us to reconsider how the cosmos builds its most mysterious giants, reminding us that sometimes the biggest answers come from the smallest beginnings. Picture the early universe not as a smooth, uniform soup, but as a fractured landscape, a place where cracks in reality itself could have given rise to black holes in the most bizarre way imaginable. This theory hinges on cosmic defects called domain walls, bizarre structures predicted by particle physics that may have formed when fundamental forces in the newborn universe froze into place like cracks in cooling ice. These weren't physical walls, but boundaries where the very laws of physics shifted abruptly, regions of space-time so warped that under the right conditions, they could have crumpled into primordial black holes. Here's how it might have unfolded. As the universe expanded and cooled just fractions of a second after the Big Bang, symmetry breaking occurred, a phase transition similar to water turning to ice. But this cosmic freezing wasn't perfect. In some areas, the transition didn't align cleanly, leaving behind defects, wrinkles in spacetime where different quantum fields clashed. Domain walls emerged as two-dimensional sheets separating these mismatched zones, each wall under unimaginable tension. Like a soap bubble collapsing, the most unstable sections could have pinched off, their immense energy density crushing spacetime until it tore open into black holes. What makes this scenario so compelling is its elegance in solving multiple cosmic puzzles at once. These walls wouldn't just form randomly, they'd trace the underlying quantum blueprint of the early universe. As they decayed, the distribution of resulting black holes could naturally explain why dark matter appears clustered in halos around galaxies. Imagine domain walls as cosmic cookie cutters. When they shattered, the black holes left behind would inherit their intricate patterns, later drawing matter into the web-like structures we observe today. The physics gets wilder. Unlike black holes born from collapsing stars or quantum fluctuations, domain wall black holes could have formed with wildly different masses, from ultralight specks to objects rivaling entire star clusters. Their diversity might solve why we see black holes across such a vast range of sizes, from tiny hypothetical ones lurking in our solar system to the supermassive behemoths anchoring galaxies. Even more intriguing, these walls might have left behind cosmic scars, subtle ripples in the cosmic microwave background that next-generation telescopes could detect, like fossilized imprints of spacetime's primordial cracks. Not all researchers are convinced, of course. Critics point out that domain walls, if too stable, would have dominated the universe's energy density, distorting its expansion in ways we don't observe. But proponents counter that certain particle physics models allow walls to decay just fast enough to spawn black holes without overstaying their cosmic welcome. Some theories even suggest these walls could have been punctured by quantum tunneling events, creating black holes at their weakest points, like holes ripping through a stressed fabric. The hunt for evidence is as creative as the theory itself. Scientists scour pulsar timing arrays for gravitational waves that might carry echoes of ancient domain wall collapses. Others model how these walls would distort the light of distant quasars, searching for telltale warping in their spectra. And if domain walls were indeed the architects of primordial black holes, their demise might have left behind another clue, a faint background hum of gravitational radiation, a whisper from the moment spacetime itself first cracked under the weight of its own imperfections. This idea does more than just offer another pathway to black hole formation. It weaves together particle physics and cosmology in a way few theories can. If true, it would mean that the universe's most enigmatic objects might owe their existence to flaws in the very fabric of reality, like cosmic pearls formed around grains of quantum sand. And that raises a profound question. Could black holes be less about destruction and more about transformation, the universe's way of stitching up its earliest wounds into something new, something that would shape everything to come? Among the most mind-bending theories about primordial black holes is the idea that they might not even belong to our universe at all. Imagine these cosmic oddities as interstellar refugees, artifacts from other dimensions or the wreckage of long-dead universes, drifting through our own like ghostly fingerprints from realities beyond our own. This is where the boundaries of physics blur into the realm of the multiverse, a hypothesis suggesting our cosmos might be just one bubble in an endless froth of parallel existences. According to some versions of string theory and eternal inflation, multiple universes could constantly be budding off from one another, each with its own unique laws of physics. When these bubble universes collide or decay, the energy released might collapse into ultra-dense knots, primordial black holes that outlive their parent realities. Picture two soap bubbles merging in midair, where their surfaces touch, tiny droplets flick outward. In this cosmic metaphor, those ejected droplets could be black holes carrying quantum imprints from their birthplace. The implications are staggering. If true, primordial black holes might encode data about alternate physics constants like gravity or the speed of light operating differently in their home universes. Some models suggest these foreign-born black holes could even defy our expectations, displaying unusual evaporation rates or emitting particles not found in our reality. Their mere existence would offer experimental proof of the multiverse, turning speculative philosophy into observable science. Supporting this idea, certain simulations of bubble universe collisions show space-time warping so violently that black holes would form naturally at the boundaries. These wouldn't be the orderly singularities we know, but twisted relics with topology shaped by their violent origins. Think of a crumpled piece of paper versus a smooth sheet. Astronomers could potentially identify them by anomalies in their gravitational signatures or unexpected radiation patterns, like cosmic accents betraying a foreign origin. Critics argue that without direct evidence, this remains a dazzling what if. But proponents counter that the math holds surprising consistency, and that primordial black holes of mysterious origin might already be hiding in our observational data, masquerading as ordinary astrophysical objects until we know how to look closer. Next-generation gravitational wave detectors could spot the telltale ringing of a multiversal black hole merger, its frequency patterns subtly off from anything our universe could produce. The beauty of this theory lies in its audacity. It suggests that searching for primordial black holes isn't just about understanding our universe's infancy. It's about cosmic archaeology, sifting through gravitational rubble for remnants of realities that might have flourished and died before our own first star ignited. And if we ever proved it, these black holes wouldn't just be mysteries. They'd be messengers carrying stories from beyond the edge of existence itself. Gravitational waves, ripples in the fabric of spacetime, have already reshaped our understanding of black holes, thanks to detectors like LIGO and Virgo catching the echoes of distant collisions. But what if some of these cosmic tremors aren't coming from the usual suspects, paired stellar black holes, but from something far older and stranger? Primordial black holes merging in the darkness could produce gravitational waves unlike anything we've observed, whispers from a time before stars even existed. The key lies in their uniqueness. Unlike black holes born from dying stars, which tend to fall within a limited mass range, primordial black holes could span from microscopic specks to objects heavier than entire star clusters. This staggering variety would leave distinct fingerprints in their gravitational wave signals. Imagine the difference between a violin's high note and a tuba's deep blast. Similarly, a merger between two asteroid mass black holes would produce waves at frequencies far higher than LIGO can detect, while a pair of mid-range primordials might create a deeper, lingering hum. Future observatories like the space-based LISA mission or pulsar timing arrays are tailor-made to catch these exotic signatures, opening a window into populations of black holes we've never seen. There's another tantalizing clue hidden in the data: the spin. Stellar black holes often inherit rotation from their parent stars, typically aligning their spins in predictable ways during mergers. But primordial black holes, forged in the chaos of the early universe, would tumble together with wild, random orientations. Their collisions would send gravitational waves spiraling out in chaotic, asymmetrical patterns, like two tops colliding mid-spin rather than two pendulums swinging in sync. Spotting this pandemonium in the waveforms could be the smoking gun that separates primordial mergers from ordinary ones. Timing adds another layer of intrigue. While stellar black holes need billions of years to pair up and collide, primordial black holes could have been merging since nearly the dawn of time. Some theories suggest their dense populations in the early universe would have made encounters frequent, meaning today's detectors might catch the last ripples from ancient collisions that occurred before galaxies fully formed. It's like listening to an echo from a concert that ended before the hall was even built. The payoff for spotting these signals wouldn't just be another entry in the cosmic catalog. Primordial black hole mergers could reveal the conditions of the universe's first second, how matter clumped, how space-time fluctuated, even how inflation might have stretched quantum wrinkles into gravitational time capsules. Each chirp, each wobble in the data would carry encoded hints about physics operating at energies no particle collider could ever reach. Yet the hunt isn't without challenges. Isolating primordial mergers from the background chorus of stellar black holes will require next-gen detectors with unprecedented sensitivity. Some researchers propose looking for statistical anomalies, clusters of mergers at improbable masses, or redshifts that defy stellar evolution's limits. Others suggest hunting for mismatched pairs, like a mountain mass black hole merging with one the size of a moon, combinations nature struggles to produce through stars alone. What makes this search so thrilling is its duality. Succeed, and we unlock a new chapter in black hole astronomy, one where gravitational waves aren't just signals but time machines carrying stories from the universe's birth. Fail, and the absence itself becomes a clue, forcing us to rethink how the cosmos distributes its hidden mass. Either way, the whispers of these ancient collisions remind us that the universe's quietest vibrations might hold its loudest truth. The early universe wasn't the smooth, homogeneous expanse we might imagine. It was a turbulent sea of density variations, regions where matter clumped slightly tighter or stretched a bit thinner. These cosmic wrinkles, faint as they were, might hold the key to primordial black hole formation. Think of it like a simmering pot of soup. Even the tiniest bubbles or ripples can grow under the right conditions, and in the case of the infant cosmos, some of those ripples could have collapsed into black holes under their own gravitational weight. What makes this theory so compelling is its connection to one of our most powerful cosmic time capsules, the cosmic microwave background. This faint glow, the afterimage of the Big Bang, carries subtle temperature variations that map the universe's density fluctuations when it was just 380,000 years old. Some of those hot and cold spots might be more than just random noise. They could be echoes of primordial black holes forming long before the CMB's light was set free. Here's how it might have worked. In the first second after the Big Bang, quantum fluctuations, tiny, random variations in energy density, were stretched to cosmic scales by inflation. Most smoothed out, but a handful of regions might have been dense enough to cross a critical threshold. Picture a hill so steep it collapses into a valley. Similarly, these overdense pockets could have crumpled inward, their gravity overpowering the outward pressure of radiation and matter. The result, black holes born not from dying stars, but from the raw unevenness of spacetime itself. The cosmic microwave background offers tantalizing hints. Certain anomalous cold spots or asymmetries in its pattern could signal places where primordial black holes formed, their gravity subtly distorting the surrounding plasma. Other clues come from the way galaxies cluster. Primordial black holes would have acted as gravitational anchors, pulling matter into structures earlier and more densely than dark matter alone can explain. But the real breakthrough would come if we could match specific CMB anomalies to black hole formation models. Simulations show that primordial black holes of certain masses would leave distinct signatures, like shadows in the microwave glow where they absorbed radiation, or faint ripples in the polarization patterns where their gravity twisted passing light. Future telescopes like the Simons Observatory or next-gen space missions could hunt for these ghosts in the cosmic microwave machine. Critics argue that the evidence remains circumstantial. After all, the CMB's variations could stem from other processes like exotic physics during inflation. Supporters counter that the sheer range of possible black hole masses means we might be looking for the wrong signals. A heavier primordial black hole would warp spacetime differently than a lighter one, and we're only beginning to map the full spectrum of possibilities. Yet if this theory holds, it would mean the universe's oldest black holes are literally written into its first light not as monsters, but as quiet imprints of a time when reality itself was still finding its balance. And that raises a profound question. Could the cosmos we see today, with its galaxies and voids, have been shaped not just by dark matter or inflation, but by the gravitational seeds of black holes we've yet to find? The answer might be hiding in the static of the Big Bang's afterglow, waiting for us to listen more closely. Deep in the universe's first moments, reality wasn't just hot and dense, it was transforming, like molten metal cooling into new shapes. One of the most pivotal shifts occurred during the electroweak epoch, when the fundamental forces we know today, electromagnetism and the weak nuclear force, split apart from a single unified interaction. This cosmic phase transition didn't just alter physics, it might have forged black holes in its wake, leaving behind primordial relics that could still haunt the cosmos today. Phase transitions are all around us: water freezing into ice, metals becoming superconductors. But the early universe's transitions operated on energies we can barely fathom. As spacetime cooled below 10 quadrillion degrees, the unified electroweak force fractured, releasing energy like cracks forming in a sheet of ice. Theoretical models suggest that in some regions, this energy release could have been so violent that spacetime itself buckled, collapsing into ultra-dense knots we'd recognize as black holes. Picture a pot of boiling water. Most bubbles pop harmlessly, but a few might trap enough steam to implode inward. The electroweak transition could have created similar gravitational pops, each a black hole birth. What sets these apart from other primordial black holes is their potential mass range. Calculations show electroweak-era black holes might weigh between 1 billion tons and an asteroid's mass, light enough to evade detection by conventional means, yet heavy enough to persist for billions of years. Their distribution would be equally unique, clustered in patterns reflecting the phase transition's geometry. Unlike inflation-born black holes scattered randomly, these might trace the ghostly lattice of where cosmic forces first fractured. The survival of such ancient objects hinges on a cosmic balancing act. Too small, and they'd evaporate via Hawking radiation long before today. Too large, and their sheer numbers would disrupt galaxy formation. But Goldilocks mass electroweak black holes could thread the needle, persisting undetected while subtly influencing their surroundings. Some theories propose they might gather in halos around galaxies, their collective gravity mimicking dark matter's effects. Others speculate they could drift through star clusters, occasionally perturbing orbits in ways that leave astronomers puzzled. Detecting them would require rethinking our observational playbook. Traditional methods like gravitational lensing struggle with objects this light, but their quantum-scale interactions might leave subtler fingerprints. For instance, if an electroweak black hole passed through a neutron star, the star's ultra-dense material could compress around it, producing faint X-ray flashes. Others suggest their Hawking radiation, though incredibly faint, might emit telltale particles like positrons, detectable as anomalies in cosmic ray surveys. Critics highlight the gaps. No direct evidence confirms phase transitions spawned black holes, and competing theories like quantum fluctuations or cosmic strings offer alternative explanations. Yet proponents argue that electroweak black holes solve two puzzles at once. They'd naturally form in the right mass range to evade current detection limits, while their predicted numbers align with dark matter's gravitational pull. The implications stretch beyond astrophysics. If proven, these black holes would be frozen snapshots of the universe's first symmetry break, offering a lab to test theories like supersymmetry or extra dimensions. Their very existence would validate that phase transitions can warp spacetime violently enough to birth singularities. a phenomenon that might recur in future cosmic evolutions or even in high-energy particle colliders. Ultimately, this theory reminds us that black holes might not just be endpoints of gravity's triumph, but byproducts of the universe's shifting identity, cosmic scars from when reality itself changed its rules. And if we ever find them, they won't just be relics, they'll be witnesses to the moment the forces that shape our existence first took their modern forms. Primordial black holes might be lurking in the cosmos not just as passive relics, but as natural particle accelerators powering some of the most energetic phenomena we've ever observed. High-energy cosmic rays bombard Earth daily, particles hurtling through space at nearly the speed of light, their origins often shrouded in mystery. While pulsars and supernova are the usual suspects, what if the real culprits are far older and more elusive? Enter the idea that tiny, ancient black holes could be cosmic ray factories, flinging particles across the universe with mind-bending force. The mechanism hinges on their extreme gravity. Even a primordial black hole no larger than a proton could wield gravitational pull strong enough to rip particles apart. As matter spirals toward its event horizon, whether interstellar gas, stray atoms, or even dark matter, it accelerates to nearly light speed, colliding with other particles in a chaotic frenzy. These violent interactions could generate ultra-high-energy cosmic rays, launching them into space like sparks from a grinding wheel. Unlike supernova, which produce cosmic rays through shockwaves, black holes would operate on pure gravitational mayhem, creating particles so energetic they defy conventional astrophysical models. One clue lies in the cosmic rays we can't easily explain. Some detections, like the infamous "oh my god" particle, a proton with the kinetic energy of a baseball pitch, carry energies so extreme that known astrophysical sources struggle to account for them. Primordial black holes, especially those clustering in the halos of galaxies, could provide the missing link. Their small size and lack of electromagnetic emissions would make them invisible, but their gravitational footprint might funnel particles into beams powerful enough to reach Earth. The math gets even wilder when you consider Hawking radiation. As microscopic black holes evaporate, they don't just fade quietly, they could erupt in a final burst of particles, including gamma rays and cosmic rays. If a population of these black holes is decaying nearby, their death throes might contribute to the cosmic ray background in ways we're only beginning to model. Simulations suggest that the combined output of countless evaporating black holes could produce a diffuse but detectable signal, like static hissing from a radio tuned between stations. Yet proving this theory means rethinking how we hunt for cosmic rays. Traditional observatories track their paths backward, searching for sources in distant galaxies or nebulae. But if primordial black holes are the accelerators, their signals wouldn't point to any visible object, just empty patches of space with unexplained particle surges. New detectors like the Cherenkov telescope array could help by pinpointing anomalies in cosmic ray directions or energy distributions that hint at hidden black hole activity. Critics argue that without direct evidence, this remains speculative, but supporters counter that the theory solves multiple puzzles at once: the overabundance of certain high-energy particles, the mysterious lack of identifiable sources for others, and even the odd clustering of cosmic rays in regions where no known astrophysical engines exist. It's a cosmic whodunit where the prime suspect leaves no fingerprints, only gravity's shadow. And that's what makes this idea so electrifying. If confirmed, it would mean the universe's most energetic particles aren't just born in stellar explosions, but in the silent, invisible grips of black holes older than stars themselves. Every ultra-high-energy cosmic ray could be a message from the dawn of time, a relic of forces so primal they shaped reality before light even had a chance to shine. Gamma-ray telescopes have long captured bursts of light so powerful they defy explanation, flashes in the void with no obvious source. Among the most puzzling is the Fermi Gamma-Ray Space Telescope's detection of an eerie excess of high-energy photons streaming from the center of our galaxy. Scientists have wrestled with this mystery for years, proposing everything from pulsars to dark matter collisions as the culprit. But there's another possibility lurking in the shadows. Primordial black holes could be the silent architects of these gamma-ray enigmas, either by devouring dark matter or triggering its annihilation in their crushing gravitational grip. Picture a black hole drifting through a halo of dark matter, its gravity pulling in particles that would otherwise sail through the cosmos untouched. Dark matter doesn't emit light or interact electromagnetically. That's what makes it so elusive. But near a black hole's event horizon, even ghostly particles can't escape annihilation. Some theories suggest that as dark matter particles collide in the extreme environment around a primordial black hole, they could convert their mass into pure energy erupting as gamma rays. It's like throwing two invisible stones into a cosmic furnace and watching them burst into flames. The math behind this idea is surprisingly elegant. Primordial black holes in the right mass range, say between the mass of a small moon and a planet, would create gravitational wells deep enough to concentrate dark matter without swallowing it immediately. These crowded zones would become particle collision hotspots, producing gamma rays at energies that match Fermi's unexplained signals. Even more intriguing, the distribution of these gamma rays aligns with where simulations predict dark matter should cluster, like a faint outline traced by something we can't see. But there's a twist. Not all researchers are convinced primordial black holes are the missing piece. Some argue that pulsars spinning neutron stars beaming radiation like cosmic lighthouses could account for the gamma-ray excess without invoking dark matter at all. The debate hinges on subtle differences in the light spectrum and distribution. Fermi's data shows a smoother, more diffuse glow than pulsars typically produce, hinting at something more exotic at work. It's the astrophysical equivalent of distinguishing a campfire's flicker from the steady glow of a city seen from space. Supporters of the black hole hypothesis point to another clue, the absence of detectable pulsars where the gamma rays are brightest. If pulsars were responsible, we'd expect to spot their radio emissions or X-ray counterparts in the same regions. Instead, the signal persists in eerie silence, as if something invisible is at play. Primordial black holes fit this profile perfectly: dark, ancient, and capable of turning the universe's most mysterious substance into light without ever revealing themselves directly. Yet the most tantalizing aspect of this theory isn't just solving the Fermi mystery, it's the double revelation it offers. If primordial black holes are indeed behind these gamma rays, they wouldn't just be illuminating dark matter's behavior, they'd be confirming their own existence in the process. Every photon could carry two secrets: the signature of dark matter's annihilation and the gravitational fingerprint of a black hole born in the universe's first moments. Future telescopes might settle the debate by mapping gamma rays with even sharper precision, searching for telltale spikes or patterns that pulsars can't replicate. Others could listen for the gravitational waves of primordial black holes merging in the galaxy's heart, their collisions ringing space-time like a bell. Until then, the Fermi excess remains a cosmic riddle wrapped in an enigma, one that might just lead us to the most elusive objects in existence and the shadowy particles they've been silently destroying for billions of years. Buried in the crushing depths of a primordial black hole could be secrets we've spent centuries trying to uncover, not just about gravity or dark matter, but about the universe's very first moments. Think of these ancient objects as cosmic time capsules, forged when reality was still a seething, shape-shifting chaos. Unlike stars or galaxies, which transform over billions of years, primordial black holes might have locked away pristine details of the infant cosmos, preserving conditions we can't replicate or observe anywhere else. Here's why this idea grips scientists. When a primordial black hole forms, its event horizon acts like a one-way vault. anything trapped inside, whether quantum fluctuations, exotic particles, or even ripples in spacetime itself, becomes isolated from the universe's evolution. It's like pressing pause on a tiny fragment of the Big Bang's aftermath, freezing it in a state untouched by the expansion, cooling, and particle interactions that shaped everything else. If we could peer inside, we might find relics of physics operating at energies so extreme they haven't existed since the universe's first trillionth of a second. The wildest possibility, these black holes could encode data about inflation, the explosive growth spurt thought to have smoothed and stretched the early cosmos. Inflation's details remain hazy. Did it happen uniformly or in bursts? Were there regions where it never ended, spawning pocket universes? Primordial black holes forming during this era might carry imprints of those processes, their masses and spins reflecting the specific conditions of their birth. Picture a tree's rings recording decades of climate history. Similarly, a black hole's properties could chronicle inflation's chaotic dawn. But how do we read a time capsule we can't open? Theorists have proposed ingenious workarounds. Hawking radiation, the faint glow emitted by evaporating black holes, might carry subtle fingerprints of what's inside. As a black hole nears its end, quantum effects could allow trapped information to leak out, like a faded message emerging from a melted piece of ice. Others suggest that mergers between primordial black holes might release bursts of gravitational waves encoded with data about their interiors, cosmic Morse code spelling out the universe's first secrets. Critics argue it's a long shot after all. Black holes are famously secretive, and quantum mechanics suggests information inside them might be scrambled beyond recognition. But supporters counter that primordial black holes, especially the tiniest ones, could operate by different rules. Their formation in the universe's quantum foam might have left them threaded with structures like cosmic strings or domain walls that preserve information in ways larger black holes can't. The implications are staggering. If even one primordial black hole yielded clues about the pre-inflation universe, it would be like finding a fossilized bubble from the Big Bang's first boil. We could finally test theories about what preceded inflation, whether alternate physics governed those early moments, or if other universes once brushed against our own. These time capsules wouldn't just tell us where we came from. They might hint at realities we've yet to imagine. And that's the paradox. The universe's most destructive phenomena could also be its most faithful historians, safeguarding truths too fragile to survive elsewhere. Whether they are hiding in deep space or drifting unseen through our solar system, primordial black holes might be the closest we'll ever get to holding a piece of creation itself. String theory paints a picture of reality far stranger than our everyday experience, a universe woven from more than just the 3 dimensions of space and one of time we know. Some models propose the existence of hidden extra dimensions, curled up so tightly that only the smallest particles can perceive them. But here's where it gets wild. These extra dimensions might have been the cosmic workshop where primordial black holes were forged under conditions impossible in our familiar 4-dimensional spacetime. Imagine gravity operating differently in the early universe. In our 4-dimensional world, forming a black hole requires compressing matter to unimaginable densities. But if extra dimensions existed during the universe's first moments, gravity could have been exponentially stronger at tiny scales, leaking into these hidden directions like water soaking through a sponge. Suddenly, collapsing matter into a black hole wouldn't need the extreme pressures of a dying star. It could happen almost effortlessly, like pinching a piece of paper into a crumpled ball instead of trying to fold an entire book. This radical idea stems from brainworld cosmology, a framework where our observable universe is a 3-dimensional brain floating in a higher dimensional bulk. In this scenario, the Big Bang's energy might have triggered gravitational instabilities that sent shockwaves through these extra dimensions, creating dense knots that collapsed into black holes. Some theories suggest these higher dimensional black holes could have later fallen onto our brain, appearing as primordial black holes with unusual properties, like masses far lighter or heavier than anything stellar processes could produce. The math reveals even stranger possibilities. Extra dimensions could have allowed black holes to form with unique shapes, their event horizons twisted into geometries that defy our 3D intuition. Some models predict black strings or black pancakes, elongated or flattened singularities that would evaporate or decay into the spherical black holes we recognize today. Others suggest these higher dimensional objects might leave behind quantum scars as they settled into our universe, subtle anomalies in their gravitational fields that next-generation detectors could spot. Experimental clues are tantalizing but elusive. If primordial black holes carry fingerprints of extra dimensions, their mergers might produce gravitational waves with distinctive overtones, additional frequencies ringing like harmonics on a guitar string. The LIGO-Virgo network has already flagged a handful of black hole collisions with unexpected mass ratios or spins, though none conclusively point to extra dimensions yet. Future observatories like the Einstein Telescope or Cosmic Explorer could have the sensitivity to catch these whispers from the bulk. Critics argue that without direct evidence, extra dimensions remain speculative. But supporters counter that primordial black holes offer one of the few testable pathways to higher dimensional physics. If we found a population of black holes with masses clustering around values predicted by these models, say, exactly 1 microgram or 10 solar masses, it could hint at the scale at which extra dimensions unfurl. Even their distribution in space might betray their origins. A higher dimensional formation mechanism could leave them clustered in ways that defy conventional cosmological models. The implications stretch beyond black holes. If extra dimensions helped seed primordial black holes, they might also explain why gravity is so weak compared to other forces, perhaps because it's diluted across dimensions we can't see. These hidden directions could even harbor their own ecosystems of particles or forces, some leaking into our universe through black hole evaporation. It's a dizzying thought. Every primordial black hole might be a porthole, however faint, to realities layered beyond our own. And that's the beauty of this theory. It turns black holes from cosmic vacuum cleaners into potential messengers, carrying news from dimensions we've yet to map. Whether they are out there or not, the mere possibility reshapes how we see the universe's hidden architecture, reminding us that the deepest mysteries often lurk where our senses can't follow. One of the most baffling puzzles in modern physics isn't about what black holes destroy, it's about what they might preserve. The black hole information paradox has haunted scientists for decades, questioning whether matter swallowed by these cosmic voids vanishes forever, violating quantum mechanics' sacred rule that information can never be lost. Enter primordial black holes. These ancient relics might not just hold the key to this mystery, they could rewrite our understanding of reality itself. At the heart of the paradox is a clash between Einstein and quantum theory. General relativity says black holes erase everything they consume, leaving behind only mass, spin, and charge, a cosmic clean slate. But quantum mechanics insists that information about particles, like their position or state, must persist in some form. It's like burning a book and claiming its words still exist, just scrambled into unrecognizable ash. Primordial black holes, especially the tiniest ones, offer a unique testing ground for this enigma because their formation and evaporation processes could expose how information slips, or doesn't, through the cracks of spacetime. Hawking radiation adds another layer. As black holes slowly leak energy, they theoretically emit random thermal noise, seemingly erasing any trace of what fell in. But if primordial black holes evaporate completely, as Hawking predicted, where does the information go? Some theorists propose these objects might encode data in their quantum structure, like cosmic hard drives storing encrypted files in their gravitational fields. Others suggest that information escapes during evaporation, imprinted in subtle correlations between emitted particles. Think of a jigsaw puzzle scattering its pieces, but with hidden clues that could reassemble the original picture. The stakes couldn't be higher. If primordial black holes preserve information, even indirectly, they'd prove that space-time has a built-in backup system, a discovery with ripple effects across quantum gravity research. String theory, loop quantum gravity, and holographic principle models all grapple with this problem, but primordial black holes could offer observational evidence. For instance, if we detected evaporation patterns in deep space that deviate from pure randomness, it might signal information leaking back into the universe, a smoking gun for theories like black hole complementarity or firewalls. Critics argue that without a full theory of quantum gravity, these ideas remain speculative, yet supporters counter that primordial black holes' simplicity, lacking the complex astrophysics of stellar black holes, makes them ideal natural labs. Their small size means quantum effects dominate, potentially magnifying information-related signals. Some even speculate that mergers between primordial black holes could release information in gravitational wave echoes, faint repeating patterns in the spacetime ripples that detectors like LIGO might one day catch. What's thrilling is how this ties to the universe's infancy. If information somehow survives primordial black holes, it means the cosmos has been keeping perfect records since the beginning, every particle, every interaction preserved in some form. That's more than a physics breakthrough. It's a philosophical revelation suggesting that nothing, not even the crushing grip of a black hole, can truly erase the past. And if we ever prove it, these ancient cosmic traps won't just be devourers of light, they'll be the universe's ultimate archivists, holding the oldest secrets in existence. Deep beneath the Antarctic ice, sensors at the Ice Cube Neutrino Observatory wait patiently for ghostly particles to whisper their cosmic secrets. Neutrinos, those nearly massless, barely interacting phantoms of the particle world, might seem like an odd place to hunt for primordial black holes. But here's the twist: when these ancient objects evaporate or collide, they could become neutrino factories, churning out bursts of these elusive particles in patterns unlike anything else in the universe. Take Hawking radiation, the slow leak of energy that dooms tiny black holes to eventual evaporation. As they shrink, they don't just emit random thermal particles. They can produce neutrinos in their final moments, a last gasp of high-energy whispers before vanishing entirely. These wouldn't be the ordinary neutrinos we see from the sun or supernova, but particles cranked up to extreme energies, carrying the unique fingerprint of a quantum spacetime disaster. For a detector like Ice Cube, tuned to catch neutrinos from across the cosmos, spotting a cluster of these high-energy events with no obvious source could be the smoking gun for a dying primordial black hole. Then there's the collision scenario. When two primordial black holes merge, the titanic forces at play don't just warp space-time, they could accelerate surrounding particles to ludicrous speeds, slinging off neutrinos like sparks from a grinding wheel. Simulations suggest these mergers might produce neutrino flares, brief but intense bursts arriving slightly before the gravitational wave signal, like thunder trailing lightning. The Kamioka Observatory in Japan and future projects like the Pacific Ocean Neutrino Experiment could catch these dual messengers, threading together gravity and particle physics in ways we've never seen. What makes this theory so compelling is the neutrino's nature. Unlike light, which gets absorbed or scattered by cosmic dust, neutrinos sail cleanly through the universe, delivering unfiltered news from the most extreme environments. A neutrino surge from a primordial black hole event could reach us from the far side of a galaxy or the edge of time itself, untouched by the cosmic fog that obscures other signals. It's like getting a pristine letter from the early universe, postmarked by gravity and stamped with quantum mechanics, critics point out the challenges neutrino detectors must sift through a constant background of noise from atmospheric particles to distant supernovae. Isolating a primordial black hole signal would require pinpointing anomalies in energy, direction, or timing that defy known astrophysics. But supporters argue that as detectors grow more sensitive and as we refine our models of black hole particle emission, the odds improve. Some even suggest that certain unexplained high-energy neutrino events already recorded by IceCube might be the first faint hints of these ancient cosmic engines at work. The implications stretch far beyond a detection. Neutrinos from primordial black holes could reveal the quantum structure of spacetime at energies no collider will ever reach. They might carry clues about how information escapes evaporating black holes or whether extra dimensions twist their properties. Every neutrino caught could be a pixel in a larger picture, one that shows us the universe not just as it is today, but as it was when reality was still knitting itself together. And that's the beauty of this hunt. It turns the most elusive particles in existence into messengers for the most enigmatic objects we've imagined. Whether they're out there or not, the search itself is a testament to human curiosity, a reach into the dark for answers that might rewrite physics itself. Ever wonder why gravity feels so weak compared to the other fundamental forces? A simple magnet can defy Earth's entire gravitational pull, lifting a paperclip as if our planet's mass barely matters. This bizarre imbalance, known as the hierarchy problem, has puzzled physicists for decades. Why is gravity a cosmic afterthought next to the mighty electromagnetic, weak and strong forces? Primordial black holes might hold a clue, offering a cosmic loophole that reshapes how we see gravity's role in the universe. The problem starts with scale. Gravity is roughly 10 to the 36th times weaker than electromagnetism, a difference so vast it feels like a cosmic typo. Traditional theories strain to explain this gap, invoking complex mechanisms like supersymmetry or extra dimensions. But here's where primordial black holes, especially those born from higher dimensional physics, could flip the script. If gravity's apparent feebleness is an illusion, a side effect of it leaking into hidden dimensions, then these ancient black holes might be the smoking gun. Picture gravity as sound in a padded room. What seems faint to us might just be vibrations escaping into walls we can't see. Primordial black holes formed in the early universe's higher dimensional chaos could carry traces of gravity's true strength, their masses and evaporation patterns betraying secrets about where the missing gravity went. One provocative idea ties this to brainworld cosmology, where our universe is a three-dimensional membrane floating in a higher dimensional bulk. In this scenario, gravity's weakness isn't innate, it's diluted, spreading its influence across dimensions beyond our perception. Primordial black holes could be artifacts of this leakage, their formation favored in epochs when gravity interacted freely with these hidden directions. If we found a population of black holes with masses clustering around a specific exotic value, say 10 to the 16th grams, it might pinpoint the energy scale where extra dimensions curl up, solving the hierarchy problem by revealing gravity's full reach. Critics argue this trades one mystery for another without direct evidence for extra dimensions. The theory remains speculative, but supporters highlight tantalizing mathematical consistencies. For instance, certain primordial black hole mass ranges would naturally emerge from higher dimensional gravity models, bridging particle physics and cosmology in ways the standard model alone can't. Even stranger, these objects might leave fingerprints in gravitational waves or gamma-ray bursts, their signals subtly warped by interactions with dimensions we've yet to map. The implications stretch beyond textbook physics. If primordial black holes confirm gravity's hidden strength, it would mean our universe's forces aren't imbalanced. They're perfectly tuned across dimensions we're only beginning to fathom. Every falling apple, every orbiting planet, every bending beam of light might just be echoes of gravity's true power, muffled by the fabric of reality itself. And that raises a humbling thought. What seems like a flaw in nature's design might be the very signature of a deeper, richer cosmos waiting to be uncovered. The story of primordial black holes might not begin in the searing chaos of the Big Bang. After all, some could be cosmic latecomers, forged in the fiery depths of the universe's very first stars. Picture a time before galaxies, before planets, when the cosmos flickered to life with its first generation of stars, monsters unlike anything we see today. These primordial stars, known as population 3 stars, were giants hundreds of times more massive than our Sun, burning hot and fast in a universe still learning how to shine. And when they died, they might not have faded quietly. Instead, they could have collapsed directly into black holes, seeding the cosmos with a second wave of primordial relics. What sets these black holes apart is their origin. Unlike traditional primordial black holes born from density fluctuations in the infant universe, these would be stellar in nature, yet not quite the same as the black holes we know today. Population 3 stars lived in a cosmic environment utterly alien to modern times. No heavy elements, no dust, just pristine hydrogen and helium. Their sheer size meant their cores reached pressures and temperatures so extreme that when they exhausted their fuel, they might have skipped the supernova stage entirely, imploding straight into black holes without the usual stellar fireworks. The result, a class of black holes with unique chemical fingerprints, lighter than supermassive ones, yet heavier than most stellar black holes, and utterly devoid of the metal-rich debris that marks later generations. The evidence for this theory lies in the gaps. Astronomers have long struggled to explain certain intermediate mass black holes, objects too hefty to form from today's stars, yet too small to fit the supermassive mold. Population 3 remnants could fill that niche perfectly. Simulations show that the first star's violent lives and direct collapses would produce black holes in the sweet spot of a few hundred to a few thousand solar masses, exactly the range we've observed in puzzling systems like HLX-1, a mysterious object lurking on the outskirts of a distant galaxy. Even more compelling, the James Webb Space Telescope has begun spotting tantalizing hints of these first stars' existence. Their light stretched and redshifted, but still carrying whispers of their helium-dominated composition. But here's the twist: these black holes wouldn't just be fossils. Their formation could have kick-started cosmic evolution in ways we're only beginning to grasp. As they sank into the centers of early gas clouds, their gravity might have catalyzed the birth of the first protogalaxies, acting as anchors for matter to cluster around. Unlike modern black holes, which often disrupt star formation with their ferocious energy output, these primordial stellar remnants could have been gentler giants, their lack of heavy elements allowing gas to cool and condense efficiently around them. In short, they might have been the universe's first architects, quietly shaping the structures that would later blossom into galaxies like our Milky Way. Yet the theory isn't without its skeptics. Some argue that population 3 stars were too rare to account for the number of primordial black holes needed to explain dark matter or other cosmic anomalies. Others point out that even these stars' death should have left some chemical trace, a faint metallicity signature we've yet to detect. But proponents counter that the earliest stars could have formed in dense clusters, their collective deaths producing black holes in numbers that rival traditional primordial models. As for the missing metals, direct collapse black holes might have locked them away forever behind their event horizons, leaving no stellar ash for telescopes to find. The hunt for answers is pushing astronomy to its limits. New instruments like the upcoming extremely large telescope could spot the ghostly afterglow of population 3 supernova or their absence, which would bolster the direct collapse theory. Meanwhile, gravitational wave observatories might catch the echoes of these ancient black holes merging, their masses betraying their exotic origins. Every clue pulls us deeper into the mystery, forcing us to reconsider not just how black holes form, but how the cosmos itself grew from darkness into light. And that's the heart of this idea. It blurs the line between primordial and stellar black holes, suggesting that some of the universe's oldest objects might be younger than we thought. Whether they're out there or not, the possibility reminds us that the early cosmos was a laboratory of extremes, where the rules we take for granted hadn't yet been written. And if we ever prove their existence, these black holes won't just be relics. They'll be living proof that even in its infancy, the universe knew how to build giants. What if every primordial black hole is less a cosmic vacuum and more a cosmic hard drive, a tiny, dense archive etched with information from the birth of the universe? This is where the holographic principle collides with black hole physics, painting a picture so radical it rewrites how we think about reality itself. The principle suggests that all the information contained within a volume of space, every particle, every force, can be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. For primordial black holes, this means their event horizons might hold a scrambled but perfect record of the cosmos' first moments, preserved in spacetime's deepest vaults. Consider how a hologram works. Shine light on a flat, patterned surface, and a three-dimensional image appears. The holographic principle argues that the universe operates similarly, with the true data of reality stored on its outer edges. A primordial black hole, forged in the turbulence of the early universe, would capture a snapshot of those conditions in the quantum fluctuations imprinted on its event horizon. Every photon, every quark that crossed its threshold wouldn't vanish. It'd be smeared into a microscopic pattern on the surface, like ink pressed onto a cosmic fingerprint. The smaller the black hole, the denser the information storage, making primordial relics potential gold mines of data from epochs we can't otherwise observe. The math behind this is mind-bending. A black hole's entropy, a measure of its information content, is proportional to its surface area, not its volume. That means a primordial black hole the size of a proton could, in theory, encode more information than all the books in the Library of Congress, compressed into a space trillions of times smaller than an atom. Researchers speculate that these objects might preserve details about inflation, quantum fields, or even the exact density fluctuations that birthed them. It's as if the universe left behind encrypted flash drives in its earliest seconds, waiting for us to crack their code. But how could we ever retrieve this information? Hawking radiation offers a tantalizing clue. As black holes evaporate, they don't just leak random noise. Theorists like Leonard Susskind suggest the emitted particles might carry subtle correlations, like pages torn from a book but still bearing traces of the original text. For primordial black holes nearing the end of their lifespans, this radiation could be a data stream from the dawn of time, a whisper of quantum states we've never directly measured. Experiments aiming to detect Hawking radiation's finer details, like its entanglement properties, might one day spot these cosmic breadcrumbs. Critics question whether such delicate information could survive billions of years of evaporation or mergers. Yet supporters counter that the holographic principle isn't about practicality. It's a fundamental feature of spacetime's architecture. Even if we never decode a primordial black hole's hologram, their existence would prove that the universe operates like a vast quantum computer, with every event horizon serving as a read-only memory chip. Future gravitational wave detectors might spot mergers where the resulting black hole's surface area, and thus its information capacity, defies classical predictions, offering indirect proof of holography in action. The implications ripple beyond astrophysics. If primordial black holes confirm the holographic principle, it would mean our 3D reality is a shadow of a deeper, two-dimensional truth, a revelation echoing Plato's cave, where what we perceive is just a projection of a richer, hidden layer. These ancient objects wouldn't just be relics, they'd be portals, challenging us to rethink whether the universe's most enduring mysteries are written in the volume of space, or on its edges, dark energy, the mysterious force accelerating the universe's expansion, remains one of cosmology's greatest enigmas. We can measure its effects, but its true nature eludes us, hiding in the void between galaxies. Primordial black holes might offer an unexpected key to this puzzle. Imagine these ancient objects as cosmic breadcrumbs, their distribution across the universe subtly warped by dark energy's relentless push. The way they cluster or disperse over billions of years could reveal dark energy's fingerprints in ways traditional telescopes can't. Here's why this connection is so compelling. Dark energy doesn't just stretch space, it influences how matter clumps together over time. Galaxies, stars, even black holes respond to its repulsive grip, their movements and groupings shaped by this invisible driver. Primordial black holes, if they exist in large numbers, would be ideal tracers for these effects. Unlike stars or gas clouds, they don't emit light or interact electromagnetically, meaning their positions reflect pure gravity and dark energy's counterforce without contamination from other astrophysical processes. It's like tracking the flow of a river by watching inert driftwood rather than turbulent foam. The critical clue lies in their distribution patterns. Simulations show that dark energy's influence would leave a specific signature in how primordial black holes spread across cosmic history. In the early universe, when gravity dominated, these objects would have clustered tightly, drawn together by mutual attraction. But as dark energy took over around 5 billion years ago, their clustering would have slowed, even reversed, as the expansion of space began to pull them apart. By mapping the density of primordial black holes at different epochs, astronomers could reconstruct dark energy's activation point and measure its strength with unprecedented precision. Gravitational wave astronomy offers a pathway to test this. Merging primordial black holes would leave ripples in spacetime detectable by observatories like LIGO or the upcoming Einstein telescope. The rate and redshift of these mergers, how often they happen, and how far away they are, could reveal whether their hosts are drifting apart faster than expected, a telltale sign of dark energy's tug. Even more telling would be spotting a drop-off in mergers beyond a certain distance, marking the epoch when expansion began outpacing gravity. It'd be like hearing fewer and fewer echoes from a canyon as the walls grow farther apart. But the true power of this idea lies in its independence from other methods. Current dark energy probes, like supernova surveys or galaxy maps, rely on complex calibrations and assumptions about stellar physics. Primordial black holes, by contrast, are minimalist. Their behavior is governed purely by gravity and expansion, cutting through the noise of gas dynamics, star formation, or magnetic fields. If their merger rates or spatial distributions deviate from predictions, it wouldn't just confirm dark energy's influence, it might expose nuances in how it operates. Is its strength constant, as the cosmological constant suggests, or does it vary over time or space? Primordial black holes could hold the answer. Skeptics rightly point out the challenges. Without definitive proof that primordial black holes exist, let alone in sufficient numbers, this remains a speculative tool. Even if they're out there, untangling dark energy's signal from other effects, like primordial black holes' own formation mechanisms or interactions with dark matter, would require exquisitely precise modeling. Yet the potential payoff justifies the hunt. Unlike fleeting supernova or faint galactic distortions, primordial black holes would offer a persistent probe, their mergers and positions accumulating data across the entire observable universe. What's at stake isn't just another measurement of dark energy's equation of state. It's a chance to see whether this force leaves unique gravitational scars on the universe's oldest object, scars that could rewrite our understanding of cosmic acceleration. And that raises a tantalizing possibility. If primordial black holes and dark energy are intertwined, finding one might finally illuminate the other, shedding light on the mystery that's been stretching our universe apart since time began. Supersymmetry isn't just another far-out physics idea. It could be the missing link explaining how some primordial black holes formed in the universe's earliest moments. This elegant theory proposes that every particle we know has a hidden, heavier twin, a superpartner waiting to be discovered. While colliders haven't spotted these elusive particles yet, their existence might have left a gravitational footprint. Black holes forged not from stars or quantum chaos, but from the decay and clumping of these exotic supersymmetric particles in the searing heat of the Big Bang's aftermath. Here's how the pieces fit together. In the supersymmetric framework, particles like quarks and electrons should have shadowy counterparts, squarks and selectrons, with properties just different enough to make them unstable in today's universe. But in the first sliver of a second after the Big Bang, when energies were unimaginably high, these superpartners would have thrived, colliding and interacting in a dense primordial soup. Some models suggest that under these extreme conditions, groups of supersymmetric particles could have collapsed under their own gravity, forming microscopic black holes without needing the crushing pressures of a dying star. Imagine a cosmic game of marbles where certain marbles are so heavy they dent spacetime itself, eventually tipping into gravitational collapse. The math reveals something even more intriguing. Unlike conventional black hole formation, which requires perfect density conditions, supersymmetry offers a loophole. Certain superpartners, like the Gravitino, the hypothetical superpartner of the graviton, might have been prone to clumping due to their unique interactions. These particles could have gathered into ultra-dense regions, like oil droplets in water, before quantum instabilities triggered their collapse. The resulting black holes would carry a distinct mass signature, potentially between a millionth of a gram and an asteroid's heft, setting them apart from both stellar remnants and inflation-born relics. What makes this theory so compelling is its dual payoff. If primordial black holes from supersymmetry exist, they wouldn't just solve astrophysical puzzles, they'd confirm one of the most sought-after extensions of the Standard Model. Their mass distribution could even hint at which supersymmetric particles were most abundant in the early universe, acting as a cosmic fossil record for physics we've yet to observe. It's like finding dinosaur bones that only make sense if a particular prehistoric ecosystem existed, except here, the bones are black holes and the ecosystem is a hidden layer of particle reality. But the hunt faces steep challenges. Without direct evidence for supersymmetry, the theory remains speculative. Critics argue that if superpartners were common enough to form black holes, we should have spotted their signatures in colliders by now. Supporters counter that the energy scales of the early universe dwarf anything our experiments can replicate, leaving room for primordial black holes to be the only surviving witnesses. Future gravitational wave detectors might narrow the gap, searching for mergers with mass patterns that align with supersymmetric predictions. A subtle nod from the cosmos that our theories are on the right track. The implications stretch beyond black holes. If supersymmetry birthed even a fraction of the universe's primordial black holes, it would mean that the answers to two of physics' biggest mysteries, dark matter and quantum gravity, might be written in the language of particles we've yet to meet. And that's the beauty of this idea. It turns the search for black holes into a backdoor probe of reality's most elusive frontiers, where every gravitational ripple could carry whispers from a hidden sector of the cosmos. Stretching across the cosmos like a ghostly fingerprint, the so-called axis of evil stands as one of astronomy's most perplexing anomalies. This mysterious pattern, etched into the cosmic microwave background, reveals an unexpected alignment of temperature fluctuations that seem to defy the fundamental assumption that the universe should look the same in all directions. Now imagine if this cosmic oddity wasn't just a statistical fluke, but the gravitational shadow of an ancient population of primordial black holes, sculpting the structure of space-time from the universe's first moments. The axis of evil emerges from subtle asymmetries in the CMB's temperature map, where hot and cold spots appear to line up along a preferred plane, almost as if the early universe had a hidden tilt. Traditional inflation theory struggles to explain this, as it predicts a far more random, isotropic distribution. But primordial black holes, especially if they formed in dense clusters or along cosmic strings during the universe's infancy, could have warped the surrounding plasma in ways that left this eerie imprint. Picture dropping pebbles into a pond. If they fell in a straight line, the ripples would carry that alignment far beyond the splash. Similarly, black holes born along a primordial filament or domain wall might have tugged the infant universe's matter into a subtle, large-scale bias that persists in the CMB today. What makes this idea so provocative is how neatly it threads together two cosmic mysteries. Primordial black holes clustering along early density filaments would naturally create anisotropic gravitational fields, subtly steering the flow of matter and radiation during the critical epoch when the CMB's patterns froze into place. Simulations of such scenarios show tantalizing matches to the axis's geometry, with black hole distributions as sparse as 1 per cubic light year, leaving detectable wakes in the microwave background. Even more compelling, these models predict secondary effects like correlated distortions in the distribution of distant quasars or galaxy rotations that align with controversial observations often dismissed as noise. Skeptics argue that the axis could still be a chance fluctuation or an artifact of foreground interference. Yet the persistence of similar anomalies, like the unexpected coherence in the CMB's largest scale modes or the puzzling alignment of galaxy spins, hints at something deeper. If primordial black holes are the culprits, their influence wouldn't stop at the CMB. Their gravitational echoes might also explain why certain galaxy clusters seem to stream toward a common point in space, a phenomenon dubbed the dark flow that conventional cosmology struggles to reconcile. The implications ripple beyond mere curiosity. If the axis of evil traces back to primordial black holes, it would mean the universe's structure isn't just shaped by dark matter and dark energy, but by an invisible lattice of ancient singularities, their collective gravity whispering across billions of years. Future CMB experiments like the Simons Observatory could hunt for the telltale shadows these black holes would cast on the microwave background's polarization patterns. A detection would do more than solve a cosmic mystery. It would rewrite our understanding of how asymmetry was woven into the fabric of reality itself. And that's the haunting beauty of this theory. The universe's most controversial anomaly might not be a flaw in our models, but a clue, a relic of black holes so old they predate light itself, quietly guiding the cosmos toward a destiny we're only beginning to glimpse. At the edge of our understanding of physics lies a chasm, a glaring gap between the realm of quantum mechanics and the force that shapes the cosmos, gravity. While quantum theory governs the dizzying dance of particles at the smallest scales, and Einstein's relativity maps the warping of spacetime by massive objects, the two frameworks stubbornly refuse to unite. This divide has haunted physicists for a century, but primordial black holes might finally offer a bridge. These relics, forged in the extreme pressures of the early universe, could be nature's own quantum gravity laboratories, testing theories in ways no particle collider ever could. Consider the unique properties that make them ideal probes. Unlike stellar black holes, which form under relatively tame astrophysical conditions, primordial black holes, especially the tiniest ones, exist in a realm where quantum effects dominate. Their minuscule size means their event horizons sit incredibly close to their singularities, creating a zone where gravity's pull is unimaginably strong yet operates across distances smaller than an atom. This is the elusive sweet spot where quantum mechanics and gravity must finally meet, a place where spacetime itself may fray into a foam of fluctuating virtual particles or reveal hidden extra dimensions. One tantalizing possibility involves Hawking radiation. As these tiny black holes evaporate, their final moments should unleash a burst of particles carrying information about the quantum structure of spacetime. Theories like loop quantum gravity predict subtle deviations in the radiation spectrum deviations that, if detected, could confirm that space is pixelated at the smallest scales, woven from indivisible atoms of spacetime. Other models, like string theory, suggest the radiation might carry echoes of higher dimensions, encoded in the particle's spin or energy distribution. It's as if each evaporating black hole is a cosmic Rosetta Stone, translating the language of quantum gravity into something we can observe. Then there's the space-time singularity itself. In a primordial black hole, the unfathomable density at its core isn't just a mathematical oddity, it's a window into how gravity behaves when it's no longer a smooth fabric but a seething quantum storm. Some hypotheses propose that these singularities might be fuzzballs, tangled knots of strings predicted by string theory, or that they could tunnel into baby universes via quantum fluctuations. The gravitational waves from merging primordial black holes might even carry fingerprints of these exotic interiors, with frequencies or ring-down patterns betraying whether the singularity is a point, a loop, or something far stranger. The experimental challenges are immense but not insurmountable. Future gravitational wave detectors, like the Laser Interferometer Space Antenna LISA, could catch mergers of black holes in the mass range where quantum gravity effects should be most pronounced. Others propose hunting for echoes in the gravitational wave signals reverberations caused by quantum structure near the event horizon. Even tabletop experiments aiming to simulate black hole physics using ultra-cold atoms or holographic setups might find clues by mimicking the conditions around these microscopic cosmic traps. What makes this quest so electrifying is its potential to turn philosophy into physics. Questions once relegated to thought experiments: can information escape a black hole? Does spacetime have a smallest possible size? Could become measurable phenomena with primordial black holes as our guides? Every unexplained flicker in Hawking radiation, every anomaly in a gravitational wave signal, might be a whisper from the universe's most guarded secret, how the infinite and the infinitesimal finally reconcile. And that's the paradox at the heart of this theory. These ancient objects, often imagined as destroyers of information, might instead be the very keys to unlocking reality's deepest layer. Whether they're proof of strings, loops, or something beyond our current imagination, primordial black holes remind us that the answers we seek aren't always in the light, but sometimes hidden in the darkest corners of the cosmos. Among black holes detected through gravitational waves and electromagnetic observations, there's a curious absence, a puzzling void separating the lightweight stellar remnants and the gargantuan supermassive beasts. Astronomers call this the black hole mass gap, a desert where black holes between roughly 50 and a few thousand solar masses should exist, yet rarely do. Traditional astrophysics struggles to explain this cosmic silence, but primordial black holes could hold the key, offering a population of intermediate mass objects born not from stars, but from the universe's turbulent infancy. The gap emerges from the limits of stellar evolution. When massive stars die, their cores collapse into black holes, but the physics of this process imposes strict boundaries. Stars below a certain mass leave behind neutron stars, not black holes, while the most massive stars tend to blow themselves apart so violently that little remains to collapse. This creates an upper limit of around 50 solar masses for stellar origin black holes confirmed by LIGO observations. On the other end, supermassive black holes, millions to billions of times the Sun's mass, dominate galactic centers. But the in-between, until recently, it seemed eerily empty. Primordial black holes sidestep these stellar constraints entirely. Formed in the early universe's chaos, they could have masses anywhere from subatomic scales to thousands of suns, with no need for stars to seed them. A subset falling squarely in the gap's range, say a few hundred solar masses, would naturally explain why we occasionally spot outliers like HLX-1, a rogue black hole weighing in at around 20,000 solar masses, drifting far from any galaxy's core. These interlopers defy stellar formation models but fit perfectly if they're ancient relics, forged before the first stars flickered to life. Gravitational wave astronomy adds another layer of intrigue. LIGO and Virgo have detected mergers involving black holes in the lower gap, those pushing 50 solar masses, but true intermediate mass events remain elusive. If primordial black holes populate this range, their mergers would produce low-frequency waves, too deep for current ground-based detectors but ideal for space-based observatories like LISA. The absence of such signals so far might not mean the gap is empty, just that we've been listening with the wrong tools. Future detectors tuned to catch these rumbling, slow-motion collisions could reveal a hidden population, THEIR Chinese letter, unlike anything produced by stellar remnants. The implications stretch beyond filling a cosmic census. If intermediate mass primordial black holes exist, they could be the missing link in galaxy formation. Simulations show that early black holes in this mass range would act as gravitational anchors, pulling together the first proto-galaxies with astonishing efficiency. Unlike their supermassive cousins, which grow by swallowing gas and stars, these primordial intermediates might have formed the universe's first dense nuclei, around which galaxies later assembled. Their presence could explain why some galaxies seem too mature for their age, as if their cores were pre-built by something older than the stars themselves. Yet mysteries remain. Why haven't we spotted more of these objects? One possibility is camouflage. Intermediate mass primordial black holes could lurk in galactic halos or float between galaxies, invisible without nearby matter to accrete. Others suggest they're rare, forming only in the densest regions of the early universe, or perhaps they've since merged, leaving behind only the echoes of their collisions in the gravitational wave background. The hunt for these gap fillers is pushing astronomy to new creative heights. Some teams scour ancient star clusters for subtle gravitational disturbances, while others model the cosmic microwave background for shadows cast by hidden black hole populations. And then there's the tantalizing prospect of black hole agriculture, watching a patch of empty space for years, waiting for a primordial intermediate to drift through and distort the light of a background star, if only for a fleeting moment. What's at stake isn't just solving a mass puzzle, it's rewriting the story of how cosmic structures emerged. If primordial black holes bridge this gap, they'd prove that the universe's architecture wasn't built by stars alone, but also by ancient gravitational seeds planted in the chaos of creation. And that would mean the black holes we see today, from the stellar to the supermassive, are just part of a far richer and more mysterious family tree. Deep in the quantum soup of the early universe, where the fabric of reality itself was still stitching together, strange defects may have formed cosmic strings, hypothetical one-dimensional cracks in space-time stretching across the cosmos like invisible wires under unimaginable tension. These weren't ordinary strings, they were flaws in the very structure of the universe, relics of symmetry breaking when fundamental forces like electromagnetism and the strong nuclear force first split apart. And according to one electrifying theory, these cosmic strings could have snapped under their own gravitational strain, fragmenting into chains of primordial black holes that still drift through the universe today. Picture a frozen lake at the crack of dawn. As the ice forms, imperfections emerge, tiny fractures where the crystalline structure doesn't align perfectly. Cosmic strings are like those fractures, but on a universe-sized scale, formed when the quantum fields governing reality cooled unevenly after the Big Bang. Some models suggest these strings would have been under such immense tension comparable to squeezing the mass of Mount Everest into a thread thinner than a proton, that any kinks or vibrations could have triggered gravitational collapse. Think of plucking a guitar string so violently it shatters into beads. Similarly, cosmic strings might have fragmented into dense knots of space-time curvature, each knot collapsing into a black hole. The math behind this idea is as elegant as it is mind-bending. Unlike black holes formed from collapsing stars or quantum fluctuations, cosmic string-born black holes would inherit their parents' extreme properties. Their masses would be tied to the string's tension, potentially spanning from microscopic scales to thousands of solar masses, all while being strung along like pearls on an invisible necklace. This could explain why some black holes appear in unexpected places far from galactic centers or in seemingly empty voids, as if they were once part of a grand cosmic filament that long ago dissolved into gravity's shadow. But here's where it gets even wilder. Cosmic strings wouldn't just passively decay into black holes, their dynamics would be a spectacle of space-time chaos. Simulations show that loops of these strings could oscillate at nearly light speed, radiating energy as gravitational waves until they finally pinch off into black holes. The resulting mergers would be unlike anything LIGO has observed. Prolonged, asymmetric events with distinctive frequency patterns, like listening to a symphony where the violins keep slipping out of tune. Future gravitational wave observatories might catch these anomalies, revealing not just the existence of primordial black holes, but the cosmic strings that birthed them. And the implications go beyond black holes. If cosmic strings seeded primordial black holes, they'd also have sculpted the universe's large-scale structure. These strings would have acted like gravitational fishing lines, pulling matter into dense filaments that eventually became galaxies. Some astronomers even speculate that the mysterious dark flow, the puzzling motion of galaxy clusters in a preferred direction, could be the ghostly tug of an ancient cosmic string network, its remnants still drifting through the cosmos like invisible puppet strings. Yet for all its elegance, the theory faces fierce skepticism. No direct evidence of cosmic strings exists, and their predicted gravitational lensing effects, sharp, double images of distant objects split by a string's passage, have never been conclusively observed. Critics argue that if strings were common enough to produce black holes, we should have spotted their other signatures by now. But supporters counter that strings could be rarer or more subtle than early models predicted, their traces hiding in plain sight within the gravitational wave background or the cosmic microwave's faintest glitches. The hunt for answers is pushing astrophysics to its limits. Teams scour telescope data for the telltale flicker of a string lensing a quasar, while others analyze the cosmic microwave background for faint, linear scars left by strings slicing through the infant universe. Even more daring are proposals to detect strings through their time dilation effects. Clocks on opposite sides of a string would tick at different rates. A distortion-precise atomic clocks might one day catch. What's at stake isn't just the origin of primordial black holes, but a window into the universe's most primordial architecture. If cosmic strings exist, they'd be the closest thing we have to visible stitches in the fabric of spacetime, flaws where reality itself is puckered from the strain of its own creation. And if those flaws birthed black holes, then every detection, every gravitational wave could be a message from an era when the universe wasn't just young, it was still learning how to hold itself together. The universe's elemental recipe doesn't quite add up, especially when it comes to lithium. According to Big Bang nucleosynthesis, the cosmic kitchen that cooked up the first light elements should have left behind about 3 times more lithium-7 than what we actually observe in ancient stars. This glaring mismatch, known as the cosmological lithium problem, has baffled scientists for decades. But here's where primordial black holes enter the mix with a startling proposal. Their explosive deaths might have been the universe's original lithium destroyers, scrubbing away this elusive element through processes we're only beginning to understand. Picture the early cosmos just minutes old as protons and neutrons fuse into the first atomic nuclei. Deuterium, helium, and lithium form in predictable ratios, except lithium stubbornly refuses to match predictions. Now imagine swarms of tiny primordial black holes peppering this primordial soup, each no heavier than a mountain but as compact as an atom. As these black holes reach the end of their lifespans through Hawking evaporation, they don't fade quietly, they detonate in bursts of high-energy particles and radiation. These final moments could have unleashed a wave of protons and neutrons with enough energy to shatter existing lithium nuclei through spallation, a process where atomic nuclei are fragmented by high-energy impact. It's like cosmic target practice, with evaporating black holes firing particle bullets that blast lithium apart into lighter elements. The numbers reveal a tantalizing fit. Calculations show that a population of primordial black holes with masses around 10 to the 12th grams a trillion grams, or roughly the weight of a small mountain, would have evaporated precisely during the epoch when Big Bang lithium was most abundant. Their death throes would have produced just enough high-energy particles to dismantle lithium-7 into helium-4 without overproducing other elements, neatly resolving the discrepancy. Even more compelling, this scenario leaves a subtle fingerprint. It would slightly boost the amount of beryllium-7, lithium's fragile sibling isotope, which later decays into more lithium, a secondary effect that aligns with some puzzling stellar observations. But the plot thickens when we consider alternative destruction pathways. Some models suggest evaporating black holes could have generated intense magnetic fields or exotic particles during their final moments, creating secondary reactions that transformed lithium into other elements. Others propose that the gamma rays from these evaporations might have photo-disintegrated lithium nuclei, stripping away protons and neutrons through pure radiative force. What's remarkable is how each of these mechanisms leaves distinct elemental signatures in the oldest stars' patterns we can now hunt for with next-generation telescopes. Critics raise valid concerns, of course. If primordial black holes altered lithium abundances so drastically, why don't we see more dramatic disturbances in other light elements like deuterium or helium-3? Supporters counter that lithium's unique nuclear structure makes it especially vulnerable. Its loosely bound nucleus is far easier to disrupt than heartier elements, acting like the weakest link in the cosmic chain. Additionally, the timing works in favor of this theory. Earlier or later, black hole evaporation would have left clearer marks on other elements, but the sweet spot for lithium destruction aligns perfectly with the black hole masses that would have evaporated during the universe's first 20 minutes. The hunt for evidence is pushing astrophysics into new territory. Astronomers now scrutinize metal-poor stars, ancient stellar relics preserving the early universe's chemistry, for correlated anomalies in lithium and beryllium that might betray this black hole intervention. Others simulate the exact particle spectra from black hole evaporations, predicting how these would alter nucleosynthesis in ways distinct from conventional astrophysical processes. Even more intriguing are proposals to search for fossil evidence in the cosmic microwave background, subtle distortions in its polarization patterns that could reflect the energy injection from countless tiny black holes dying in the cosmic dawn. What makes this theory so compelling isn't just its potential to solve the lithium problem. It's the way it turns primordial black holes from passive relics into active participants in shaping the universe's chemical evolution. If correct, it would mean these ancient objects didn't just witness the first moments of creation. They rolled up their sleeves and fundamentally altered the cosmic recipe. And that raises a profound question. If lithium's scarcity is indeed a scar from evaporating black holes, what other elemental anomalies might be hiding in plain sight, waiting to reveal the fingerprints of the universe's most enigmatic architects? Stretching the boundaries of known physics, some theorists propose that primordial black holes might be more than just cosmic traps. They could be the universe's ultimate shortcuts. Imagine a black hole so ancient and dense that its gravitational grip doesn't just warp space, but stitches it into a bridge to another time or place. These hypothetical structures, known as traversable wormholes, have long been the stuff of science fiction, but primordial black holes could offer a natural mechanism to stabilize them, turning speculative fantasy into plausible cosmic architecture. The key lies in their formation. Unlike stellar black holes born from collapsing stars, primordial black holes emerged in the universe's first moments, when extreme densities and pressures could have created exotic spacetime geometries. Under the right conditions, a pair of these black holes might have formed with their interiors connected by a throat, a tunnel of distorted spacetime shielded from collapse by negative energy or repulsive forces. Think of it as a cosmic hourglass with two black holes as the bulbs and a narrow passage threading between them. This wormhole wouldn't just link distant points in space. It could theoretically allow matter or information to traverse vast distances instantaneously, defying the speed of light limit. What makes primordial black holes especially compelling candidates for wormhole generators is their potential quantum stability. Tiny black holes with masses comparable to asteroids or less might have avoided the crushing gravitational forces that would typically snap a wormhole shut. Some models suggest their quantum fluctuations could generate the negative energy densities needed to prop the throat open, like microscopic springs pushing against the walls of a collapsing tunnel. Even more intriguing, if these wormholes formed during inflation, the universe's rapid early expansion, they could have been stretched to macroscopic sizes, lurking undetected in today's cosmos like invisible subway lines threading through spacetime. The math behind this idea is as beautiful as it is daunting. Einstein's equations allow for wormhole solutions, but they require exotic matter with negative energy to prevent the tunnel from pinching off. Primordial black holes, with their roots in quantum gravity and higher dimensional physics, might sidestep this hurdle. String theory, for instance, posits that cosmic strings or brains, higher dimensional objects left over from the Big Bang, could intersect with primordial black holes, creating the tension needed to stabilize a wormhole's throat. It's as if the universe's most enigmatic objects were pre-wired with hidden backdoors, waiting for the right conditions to unlock them. Observing such a structure would be a challenge bordering on the impossible. Wormholes wouldn't emit light or radiation, and their gravitational signatures might blend seamlessly with ordinary black holes, but there are subtle clues physicists hunt for. If a primordial black hole acting as a wormhole mouth passed between Earth and a distant star, the star's light might flicker in unexpected ways, first dimming as the black hole's gravity lenses the light, then brightening as the wormhole's throat refracts it. Mergers between wormhole-connected black holes could also produce gravitational waves with bizarre echoes, as if the signal were bouncing through a hidden chamber of spacetime before reaching our detectors. Skeptics rightly point out the speculative leaps involved. Negative energy, stable wormholes, and cosmic shortcuts remain unproven, and many solutions exist only on paper. Yet the mere possibility reshapes how we view these ancient objects. Primordial black holes wouldn't just be remnants of the early universe, they'd be potential gateways, silent architects of a hidden cosmic subway system woven into the fabric of reality. And if they're out there, the universe might be far more connected than we ever dared imagine. What if the universe isn't what it seems, not a physical cosmos, but an unfathomably complex simulation running on some cosmic-scale computer? This radical idea, known as the simulation hypothesis, suggests our reality might be an elaborate digital construct. And here's where primordial black holes enter the conversation. These enigmatic objects could be more than cosmic oddities. They might be glitches in the code, artifacts left behind by the universe's renderer, or even deliberate signatures placed by whoever or whatever built this virtual reality. Think of a video game encountering a processing error, a texture that fails to load properly, leaving behind a strange, unnatural void. Primordial black holes could be the cosmic equivalent, regions where the simulation's physics engine struggles to compute the complexity of spacetime, defaulting to a crude but stable solution, a singularity. Unlike stellar black holes, which form through predictable in-game mechanics like collapsing stars, these ancient objects might correspond to memory allocation errors in the early universe's initialization sequence. Their seemingly random mass distribution and uneven clustering could reflect buffer overflows or data compression artifacts from the first moments of runtime. The timing adds another eerie layer. Primordial black holes form in the universe's opening microseconds precisely when a simulation would be most computationally strained, booting up countless variables simultaneously. Under this crushing processing load, rendering errors might manifest as microscopic density spikes collapsing into black holes. Some theories even suggest their evaporation via Hawking radiation could be the simulation's garbage collection protocol, cleaning up unstable quantum computations before they crash the system. But perhaps the most provocative idea is that these black holes aren't mistakes at all. They could be intentional markers, cosmic Easter eggs left by the programmers. Just as game developers hide messages in the code, primordial black holes might encode information about the simulation's underlying architecture. Their gravitational wave signatures could carry patterns resembling error correction algorithms or data packets, hinting at the universe's resolution limits. If we ever detect a merger with inexplicably precise mass ratios, say, black holes weighing exactly pi or the golden ratio times a solar mass, it might be a breadcrumb trail pointing toward the simulation's mathematical framework. Critics dismiss this as speculative fiction, arguing there's no way to distinguish a glitch from natural phenomena. Yet supporters counter that certain anomalies like black holes with impossible spins or energies that defy entropy could act as red flags. Future gravitational wave observatories might spot mergers where the resulting black hole's temperature or information retention violates standard physics, behaving more like a corrupted data packet than a celestial object. Even the infamous axis of evil in the cosmic microwave background, an unexplained alignment of temperature fluctuations, could be a rendering artifact, the simulation's equivalent of a stretched polygon in a poorly optimized game. The implications spiral into existential territory. If primordial black holes are simulation artifacts, their existence might imply that spacetime itself is pixelated at the tiniest scales, with black holes acting as cosmic debug tools that expose the grid. Quantum fluctuations around their event horizons could reveal the universe's frame rate, while their evaporation might uncover the simulation's data deletion protocols. Some theorists take this further, suggesting that advanced civilizations within the simulation could even manipulate these black holes to send messages to the underlying base reality, or to hack the system itself. Whether this theory holds water or not, it stretches our perspective to the breaking point. Primordial black holes might be more than remnants of cosmic dawn. They could be the universe's way of whispering that there's a layer of reality we've yet to glimpse, hiding in plain sight behind the curtain of gravity. And that leaves us with an unsettling thought. If we ever prove they're glitches, what does that say about everything else we think we know? From cosmic dark matter architects to potential wormholes stitching the fabric of space-time, primordial black holes have taken us on a journey through some of the most electrifying frontiers of physics. Whether they're the invisible scaffolding holding galaxies together, the missing seeds of supermassive giants, or relics from a multiverse beyond our own, each theory we've explored reshapes our understanding of reality. These ancient enigmas don't just fill gaps in our cosmic knowledge, they tear open new questions about the universe's origins, its hidden structures, and even the fundamental laws that govern existence itself. What makes these theories so thrilling isn't just their audacity, but their power to connect seemingly unrelated cosmic puzzles. The same primordial black holes that might explain dark matter's grip could also account for bizarre gravitational wave signals or lithium's mysterious scarcity. They bridge quantum mechanics and relativity, particle physics and cosmology, threading together disciplines that often operate in isolation. And in doing so, they remind us that the universe is far stranger and more interconnected than we ever imagined. Yet for all we've theorized, the most exhilarating truth remains: we're still at the beginning. Every unanswered question about these cosmic ghosts, do they really exist? How many are out there? What secrets do they hold? Is an invitation to keep exploring, to peer deeper into the darkness where the universe guards its oldest mysteries. Because the day we definitively find them or rule them out won't just close a chapter in astrophysics, it'll rewrite the story of everything, so stay curious. The cosmos is full of whispers waiting to be heard, from the faintest Hawking radiation to the echoes of black holes colliding across time. If you're as captivated by these enigmas as we are, hit subscribe, because the next cosmic revelation is always just one discovery away, and we'll be here to dive into every twist and turn. After all, the universe's greatest stories aren't just written in the stars, they're hidden in the shadows between them. Let's keep searching.